One of the first parametric equations we learned to use to sketch a curve involved trigonometric functions to define a coordinate on a circle. The equation for a circle centered at the origin is x squared plus y squared equals r squared, where r is the radius of the circle and xy is a general point on the circle. If we define theta to be the angle the line from the origin to xy makes with the positive x-axis, we can define x and y with the following: x equal r cosine theta and y equal r sine theta. Furthermore, if we set the radius to be a constant, then we have defined x and y to be functions of another variable, a parameter, theta. Ellipses can also be described by parametric equations. When we use parametric equations, the difference between ellipses and circles is due to the number being multiplied by the sine and cosine functions. With the circle, we recognize this number as the radius r, but with the ellipse, there is no radius. On an ellipse, there is a major axis and a minor axis, as seen in this general ellipse centered at the origin. The equation for this ellipse is x squared over a squared plus y squared over b squared equal 1. And we can write parametric equations for a point xy on this ellipse as x equal a cosine theta and y equal b sine theta. A curve that is closely related to an ellipse is a Lissajous curve, which we briefly saw in the video on frequency beats. Lissajous curves have the following parametric equations: x equal a sine of 2 pi f1t minus phi, and y equal b sine of 2 pi f2t. With these equations, we see that x and y have different amplitudes, a and b, different frequencies, f1 and f2, and x has a phase shift, phi. Each of these are constants, which means the only parameter is t, which stands for time. We will observe these curves on an oscilloscope and hear them by listening to sine waves. The amplitudes for the sine waves are set by volume control, and the frequencies will be measured in hertz, which stands for cycles per second. First, the circle. We need the phase shift to be phi equal to pi over 2, which makes the sine wave a cosine wave, and we need the amplitudes and frequencies to be the same. In the graph, the green and blue waves are out of phase, and the white circle in the middle is created by plotting the xy coordinates from the parametric equations. Next, the ellipse. Keeping the phase shift and frequencies the same as for the circle, if we change the amplitudes to be different from each other, we get an ellipse. If I decrease the volume for the x-coordinate sine wave, the vertical axis is elongated. If I decrease the volume for the y-coordinate sine wave, the horizontal axis is elongated. If we set the phase shift to be phi equal to 0 or pi, we get a line. With the phase shift set to 0, the waves add together and get a combined louder sound than just one wave. But with the phase shift set to pi, the waves cancel each other out and we hear no sound. If the ratio of frequencies f1 over f2 is equal to 2, then we get a parabola that opens left or right, depending on the phase shift. The green graph at the top has a frequency that is twice as much as the blue graph at the bottom. If I flip the phase, then I will change the direction of the parabola. And now let's reciprocate the frequencies to see parabolas that open up or down. In the video on frequency beats, we saw an animation of the circle seeming to rotate in 3 dimensions. This was caused by setting the frequencies so they differed by 1. If we make the difference larger, the rotation is faster. Even just a difference of a couple more than 1 becomes quite fast. We can create other still images by using ratios of other smaller numbers. These ratios also relate to harmonic intervals found in musical scales. Here's the ratio of a perfect fourth, where the frequencies are at a ratio of 4:3. Next, the perfect fifth, where the ratio of frequencies is 3:2. And then finally, the octave above a perfect fifth, where the frequencies are at a ratio of 3:1. These Lissajous curves are used to help test electrical equipment. For example, while I intentionally set the two waves to be out of phase at certain points to see different images, we could also discover that two waves are out of phase by looking at the Lissajous curves from the two waves.